Okay. So lesson 23 is actually closely related to lesson 22, which is symmetrical components. So in lesson 22, we saw that any vector, whether balanced or unbalanced, can be represented by means of a combination of positive sequence, negative sequence, and zero sequence. Okay. Now that is for theoretical perspective, but how it helps us in determining the fault current for a for an unsymmetrical fault. So for that, we need to develop sequence networks of various components of the power system and connect them so as to compute the fault current for unsymmetrical faults. So what we will see? First, we will see the sequence networks of various components. Okay, so we will have an overview. So power system elements. So we are going to develop the sequence network for power system elements such as transmission line, transformers, and synchronous machines have three-phase symmetry. Okay. Therefore, when return currents of a particular sequence are passed through these elements, voltage drops of the same sequence appears. Each element can therefore be represented by three decoupled sequence networks. So, we will develop three decoupled sequence network for transmission lines, transformers, and synchronous machines on a single phase basis. Okay, and what are these three decoupled networks? Positive, negative, and zero sequence network, which respectively can then be suitably interconnected to simulate different unsymmetrical faults. So that is our objective. The objective is to simulate different unsymmetrical faults. Okay. A fully transposed transmission line is completely symmetrical, and therefore, so we start with transmission line. A fully transposed transmission line is completely symmetrical, and therefore the per phase impedance offered by it is independent of the phase sequence of a balanced set of currents. In other words, so mind it, you may write it down. In other words, the impedances offered to positive and negative sequences currents are identical. So for a transmission line, the transposed line, we are meaning transposed line which are practically available. So for a transmission line, the positive and negative sequence impedances or networks are identical. Okay. Next, when only zero sequence currents flow, the current in each phase is identical in both magnitude and phase angle. Part of the current return via ground, while the rest return through overhead return wires. So it is not of significance. So we'll see sequence impedance. So this is the derivation of the sequence impedance of the transmission line. So as you know, as you see here, we present here a three-phase line with phase currents IA, phase current IB, phase current IC. So these are the three phases, and each phase has equal impedance or reactance XS, we are neglecting resistance, which is self inductance and mutual inductance XM. Okay, and that is a return path, a return line, which is where the neutral current flows. This is the neutral. Okay, three phases and one neutral. So we can have a network equation for this case, and we will find that the positive, negative, and zero sequence network or impedance of the transmission line are given by this. So these are the positive, negative, and zero sequence impedance of the transmission line. So which are XS, as we saw in the very first slide, that positive and negative sequence impedances of the line are identical, JXS minus XM, JXS minus XM, whereas the zero sequence impedance is JXS plus 2XM. What are XS and XM? XS is the self impedance, self reactance, and XM is the mutual impedance or mutual reactance. So based on this, we can have the sequence network of a transmission line. So this is the sequence network of a transmission line. So for any transmission line, you will show the transmission line by means of such sequence networks. Okay. So that you will have to use while computing the unsymmetrical fault currents. Okay. Okay. So transmission lines are over. So what is the conclusion? That positive and negative sequence impedances of a transmission line are identical and zero sequence impedance is XS plus 2XL. Now we'll see for generators. This is very important. Consider an unloaded synchronous machine grounded through a reactor Zn where EA, EB and EC are induced EMF in all the three phases. So these are the induced EMF, EA, EB and EC. A fault at machine terminal results in currents IA, IB and IC in the three lines irrespective of where the fault occurs. If the fault involves ground, then a neutral current will flow through the ground impedance, okay, neutral impedance. For fault analysis, the equivalent circuits of the machine to the flow of the positive, negative and zero sequence current must be used for unsymmetrical faults. Since a synchronous machine is designed with symmetrical windings, it induces EMF of positive sequence only. That means the EMF will be there only in the positive sequence network. With the flow of negative sequence current, the rotating field in stator is created, which rotates in the opposite direction of the positive sequence field at double the synchronous speed. Since the negative sequence MMF is alternatively presented with the quadrature reluctance, so the negative sequence impedance, the numerical value, you can obtain this. So as we have discussed, we generally take subtransient reactances because we need to know the maximum current. Okay. So eventually we get the following sequence networks of the generators. So what you see here is, first one is the normal impedance diagram of a generator with three phase. This is phase, this is another phase and this is another phase. See, each phase has a voltage source, okay, because it is generating three phase voltages and there is a neutral reactance. However, when you show the positive sequence network of the generator, which is this is the positive sequence network of the generator, you show an EMF source, okay. Whereas if you see the negative and zero sequence network, okay, so I would suggest you draw this positive sequence network, which is one EMF source EAN per phase and an impedance Z1, which is the positive sequence impedance. Then the negative sequence impedance has no EMF source connected to it. The negative sequence network of the generator has no EMF connected to it because the EMF generated in the machine is positive sequence only because of the synchronously rotating magnetic field, okay. And zero sequence network, as we discussed, it contains the zero sequence impedance as well as 3 times the neutral impedance. So it is Z0 plus 3 times Zn. So these three combined give you the positive, negative and zero sequence network of the generator, okay. Then coming to transformers, the next component that we will discuss is transformers. We discussed transmission line. What is the characteristic feature? That positive and negative sequence impedances of a transmission line are equal. For what is the feature for the generator? That the EMF source will be there only in the positive sequence network and the zero sequence network will have the neutral impedance 3 times Zn, okay. What about transformers? Typical value of sequence impedances for a 5 MVA 6.6 kV 3000 rpm turbo generators are 12%, 20%, 10% or 1.2 per unit, 0.12 per unit, 0.2 per unit, 1.1 per unit, okay. These are for generator, okay. Whereas the positive sequence series impedance of a transformer equals its leakage impedance, okay. So positive sequence impedance means the leakage impedance. Since transformer is a static device and there is a rotating magnetic field, the leakage impedance does not change with alternation in the phase sequence, okay. So it simply says that due to the absence of any rotating field, the positive and negative sequence reactance of the transformer are same and that is the leakage impedance, okay. Assuming transformer connections allowing zero sequence currents, zero sequence impedance is offered different from positive and negative. So you see only zero sequence component will be different. Okay, so that we'll see, and that will depend on the transformer connections. When magnetizing current is neglected, transformer primary would carry currents only if there is current flow in the secondary side. So the point to take is from here that the positive and negative sequence impedances of a transformer are equal to its leakage impedance, whereas the zero sequence impedance depends on the transformer connection. Okay, so as you see here, we'll discuss one by one. So how many connections? We will show 5 such connections. Okay, we'll show 5 such connections. So if you see here, so this is a star-star connection with both stars grounded. Okay, and this is the actual connection, and this is the sequence impedance, zero sequence impedance. Okay, this is the zero sequence impedance. Similarly, this is the star grounded but star open. Then in this case, this is the connection. Okay, so here there is a gap because there is no ground connection on the secondary side. Is the star grounded delta connection. So if you see here, this is the connection. Okay, this is the sequence network, zero sequence network. Okay, then in this case is star delta, no grounding, and this is the sequence network. Okay, similarly this is delta delta, no grounding, and hence this is the sequence network. Okay, so what is the significance? The significance is that during unsymmetrical fault computation, you need to use this particular connections for sequence networks. Okay, okay. Now this is one problem. Okay, question number 4.2.2 that you have to solve at home. Okay, so this is for this question we have developed the positive sequence network and negative sequence network. I have given the reference of the book also. Similarly, question number 3. Question number 3, we have developed the zero sequence network. So you see here, for this particular circuit, the zero sequence network is given by this. Okay. Similarly, question number 4.2.4. Okay, I think this is the normal sequence zero sequence network, and this is another zero sequence network example with this transformer connections. Okay, so you in class you may not be able to solve it in detail, so we'll see these problems. Okay, we'll directly go to the okay. We can see here, have a look where we are. We did some problems related to symmetrical fault computations. Okay, all these problems we have done in the class. Now the question number 1 is related to the symmetrical components. The solution is given in the PPT. Now what I just shown you is question number 2, question number 3 and question number 4. Okay, so as you see here, what is the problem asking? The problem asking, draw the sketch the zero sequence network. Okay, okay, so draw the zero sequence network. Okay, and here it is showing draw the positive, negative and zero sequence network for the system. So all these solutions I have given you in the PPT. So you are suggested to practice all these problems. Next class we will use this sequence network and see how this can be used for unsymmetrical fault computation.